non-ideal effect that one needs to consider in actual MOSFET is the body effect. Okay, so what it says is that if you recall in the previous NMOS PMOS structures, we were having this bulk or the semiconductor material. We're keeping this the terminal of this short circuited with the source, and both were at the ground. Both of the terminals were grounded. Okay, but situation is different. If, for example, in this figure 21, you have two NMOS devices. Okay, why NMOS? Because you see you have two transistors. Okay, M1 and M2. Both are having their drain and source terminals. For M2, you have D2, you have S2. Okay, then you have the gate. So let's call this gate over here as G2. Then you have a gate G1 for M1, and you have D1 and S1 for the drain and source terminals of the transistor M1. What happens is that you cannot, if you need to turn both the transistors on so they conduct. If they conduct, then you need a channel. You need to create a channel such that you are going to apply a VDS. Okay, you need a horizontal electric field as well, besides establishing a vertical electric field due to the gate supply. So the problem that occurs is that your sources are not at ground no more. That why it happens is that you see for this terminal. Look at this terminal. What is happening over here is that this is the source terminal for the transistor M2, but this also acts as a drain terminal for the transistor M1. So that means for this transistor to conduct, it should be connected to a positive VDS supply battery. Okay, so in that case, the source of transistor M2 is not much is not likely to be at the ground potential. Okay, it is at some potential higher than the ground potential. So what happens is that you see the situation is, well, this is a p-type substrate and it's common to both M1 and M2 transistors. Okay, this is a p-type substrate for both NMOS transistors. So well, you do have a inverse or a reverse bias p-n junction across this n-doped regions of drain and source. Well, that's there, but the thing is the source over here is grounded. Okay, so it has a different depletion width or a different call it a space pre-charge region. Okay, depletion width. But once you are going to drive this D1 for transistor M1 to conduct, once you are going to establish an electric field at D1 by reverse biasing this p-n junction, then this depletion width is going to increase. Okay, this might go like this. And what this is going to do is, look at this source. This is grounded. Okay, this is grounded with this substrate. But once you're going to apply a positive supply, your channels are going to be tapered off at the drain terminal for M1, and then at the source terminal at your for M2 transistor. Okay, so your channel widths are going to be modulated. Okay, and due to the modulation of channel width, if you recall previously, what happened is that your threshold voltage is going to change. The threshold voltage that is required at the gates G1 and G2 is going to change. Okay, that's the minimum voltage required to establish a channel. But owing to, I mean, since VDS, this VDS is going to change the depletion width, so you have different depletion widths at the sources. Okay, S2 and S1. So the channel cannot be considered as having the same length as the length of that metal gate at G1 and G2. It's different. Okay, and if you consider the pinch-off effects, well, in actual MOSFET, as we have talked earlier, um, in the finite output resistance, this point can move forward. Okay, this point can move forward, resulting in a channel width modulation, resulting in more non-idealities to be considered. So it makes the analysis of transistor bit more difficult. We can keep this out of our analysis, but it's good to know that in actual MOSFETs, if you have an integrated circuits having two NMOS configurations on one IC like this, well, then your threshold voltage is going to be affected. Okay, so up to this point in our discussion on MOSFET series lectures, we have assumed that the substrate or the body is connected to the source. Okay, well, that's the case over here. That's true. For this bias condition, the threshold voltage is constant. Okay, but in IC, however, the substrate of all the N-channel MOSFETs are usually common and are tied to the most negative potential in this circuit. Okay, but now we don't have this common source. This is also the drain that is being shared by another series NMOS. So an example of two N-channel MOSFET is shown in figure 21. So we have two N MOSFETs fabricated in series on the same substrate. Substrate is your bulk, or this is also semiconductor material. Okay, so the source terminal S2 source terminal S2 of the transistor M2 is more than likely not at grounded potential for transistor to conduct. So what's happening is that P-type substrate is common to both transistors. The drain of M1 is common to the source M2. When two transistors are conducting, there's a non-zero drain to source voltage on M1. So what it means is this is your transistor M1, so drain to source voltage, there has to be a drain to source voltage, and you have to apply VDS over here as I've talked earlier. So which means that the source of M2 is not at the same potential as the substrate. So, well, that's the case. Your your source S2 over here is not no more grounded. Okay, this shares the same potential as VDS over here, as VDS. So these bias conditions means that a zero or a reverse bias voltage, it exists across the source and substrate PN junction. So, well, yes, we have from the substrate to the source, we have a reverse bias PN junction due to the positive terminal of the VDS battery, and this depletion width, how much it's the width or the charge density over here is will now be controlled by the VDS. Okay, so so the change in the source and substrate junction voltage, it changes the threshold voltage. This is expected, and this is called the body effect. The same situation exists in the p-channel device. So, for example, consider n-channel devices, which we have seen earlier. Okay, now this is the figure. If you consider the schematic, this is figure 22. You have a positive gate source voltage for NMOS. This is n-channel enhancement mode, so you need a positive gate to enhance or to produce an inversion layer for the transistor to conduct. So these dotted lines are showing this. This is enhancement mode. Okay, just to recall what we have discussed previously in the circuit symbol convention videos. So you have a positive. Look over here. You have the source is positive due to positive VDS, and the bulk is negative. Okay, previously we didn't have this positive and negative terminals established at the bulk between the bulk and substrate. Both bulk and substrate were grounded. This arrow is showing the direction of PN, and that's towards the oxide. Remember, this was the oxide, and this solid line is the gate metal. So this is oxide, OX. So you see, this is your P-type substrate. This is N-type region. So the arrow should be like this, PN junction. So this is what is being shown. But the only difference in this circuit schematic is showing that the source is at positive with respect to the bulk. Okay, so they were supposed to be at the same potential. Due to this, your length is modulated. Okay, your channel length is not the same as for the ideal transistor. So what happens is that to maintain a zero, okay, so this is shown in figure 22. To maintain a zero or reverse bias source substrate PN junction, we must have VSB greater than or equal to 0. So since we are reverse biasing the junction over here through VDS, and VSB is greater than 0, this is S, this is B, so this is B, this is S. So of course your over here VSB has to be greater than 0, because the doping of the semiconductor is such that S is doped by the negative charges, and this is consisting of positive carriers, mobile carriers. So VSB has to be greater than 0. So this junction is reverse biased. Okay. So for a reverse bias junction, to maintain a zero reverse bias uh, source substrate PN junction, we must have VSB greater than or equal to 0. If VSB is equal to 0, well, okay, if VSB equal to 0, then you see in this expression, look at this expression, that is giving the threshold voltage. If VSB equal to 0, then VTN is VTNO, where VTNO is the threshold voltage. Okay, so VTNO becomes equal to VTN if your VSB is equal to 0. Well, but for a non-zero VSB, the threshold voltage for this condition is given by this relation. This is for non-zero VSB. Gamma is the body parameter or the bulk effect. This gamma over here is called the bulk threshold or the body effect parameter, and it's related to the device properties. Okay, it's typically on the order of 0.5 square root of voltage. So it's like this, 0.5, the units like this, square root of volts. Why square root of volts? Because you see this VSB is also in volts. Okay, phi of f over here is a semiconductor parameter. It typically depends on the doping as well. The order is 0.35 volts. So whatever it comes, it's in volts. Square root of the volts, volt under root. Okay. So gamma is also the dimensions are as such for the gamma. This is also it's of the order of 0.5 square root volt. So square root into square root is volts. That you can add in VTNO, and that VTN comes in volts. Okay, so VTN is still in volts, but these two quantities are under. This is under volts. The units are like this, and this quantity, whole quantity, is also into volts. The product is volts. So, so it's a function of semiconductor doping. This phi of f is a function of semiconductor doping, and the magnitude order is given as 0.35 volts, and your gamma parameter is 0.5 volts. So you note in this expression, for a non-zero VSB, if your gamma increases, what happens if your gamma increases? If your gamma increases, the threshold voltage increases. Okay, so gamma is like modulating your parameter, the threshold voltage. Okay, it's just like the channel modulation. And that's physically what is going on in over here. Okay, this source region is not connected to the substrate, and this source is more positive than the bulk. So you are creating a more negative or reverse bias PN junction, and due to this reverse bias PN junction, your channel must be tapering off. Okay, so its length might be being modulated or changed. So due to this, your threshold voltage is being changed. So this is all because of non-zero VSB. If VSB is 0, well, this is under 2 phi minus under 2 phi, and you still get VTNO, which is equal to VTN. All right, no problems. But this problem occurs due to the reverse biasing of VSB and the source getting the supply from VDS. All right, so source is not being short circuited to the bulk. So your threshold voltage is going to change. If you're not going to maintain the source at the same potential as the bulk, well, you are going to have a body effect. All right. So this is a complicated effect related to the MOSFET in actual MOSFETs. If you're going to consider that in the analysis. Okay. So we see from the publication that the threshold voltage in n-channel devices, they increase due to this body effect. So as this parameter gamma grows, the threshold voltage in the n-channel devices, they tend to increase. Okay, so this is like controlling, this parameter is controlling your VDN, right? Now this body effect can cause a degradation in the circuit performance because of the changing threshold voltage. Okay, it's also modulating the channel length. So in general, we can neglect this body effect, okay, in our circuit analysis for simplicity. So we will consider that this bulk, semiconductor surface, substrate, and the source terminal are still at ground. So to just alleviate this problem, you can just connect them and ground them. Okay, but for a fabrication of an IC like this, well, you cannot neglect the bulk effect, or you cannot ignore the body effect. Okay, so for the body effect, for the analysis, you need to consider the change in the threshold voltage where the transistor is going to turn on, and you need to consider how much VSB is there, and that is going to determine how you are going to change how your VTN is being determined from VSB and from the gamma parameter.